morning, ladies and gentlemen. My name is Ngô Hoàng Nguyễn and I'm a student at International University. So today I would like to present my paper is a patch antenna for the SM application. So the content of today is divided into three parts. First, introduction. Second, design step. And third, the results. So if you have any question, please feel free to ask me at any time, or you can wait until the end of the presentation and ask me then. And the presentation will last about 10 minutes. Let's start with the first part, introduction. So the mobile networks are very common in the world and in Vietnam. So telecommunication use 2G and 3G for the communication. Recently, Vietnam government want to equip the GPS black box for public and business transportation. So the challenges in designing antenna is they cover the GSM frequency bands and the size is more to fit into the black box. So the research objective is to design and implement the bus antenna that integrated onto the PCB board for GSM applications. And the design requirements are working in GSM 850, 900 and 1800 MHz. The return loss is lower than -10 dB. The mount size 40 mm in its dimension, with the thickness is about 1 mm, and it is integrated onto the PCB board. So let's start with the design step. First, we researched and identified a common GSM antenna for publication. Then we accept SS to design the GSM antenna to be smaller, and then we implement PCB board and we do the measurement on the real antenna. So it is some publication we found. The first one is the antenna was created by Jiang Wu Zhang. You can see that this is the -10 line. This antenna can work well at this frequency, but the size is 40 and 7 mm, so the thickness is so large that we cannot integrate it onto the PCB board. The second design is 2J540 PCB antenna sector. You can see that and the frequency is lower than -10, but also the size is also large, 112.9 mm. And the third is pentaband standalone PWB antenna, created by Burns Technitron company. You can see that the size is small, 40, 15, and 7 mm, but the S11 is nearly -10 dB. And the last one is 2J0S5, was created by antenna conceptor. You can see that this antenna is very small. The size is 35.1.15 and 1.7 mm, but the return loss is nearly -6 dB. So based on this antenna, we create our own antenna. Our antenna is can be divided into 4 parts. The first part of 8 is to control the fixed impedance. Part C is to shift the resonance frequency at 850 and 900 MHz. And part B, 3 fingers, and part D, 2 horns to lower the return loss. And I will show you the result. The matching picture, frequency, lower S11, the radiation current, and the design we sent to the BN Robotics company. So this is our first design. You can see that the pitch is short, and this is the -10 threshold line. So at 900 MHz, it is lower than this line, and you can see that this is the Smith track. this frequency is not matched to the 50 ohm. So we, with the second design, we make the 50 longer to 1 meter long, and you can see that at this in this figure, and the 1800 megahertz is matched to the 50 ohm, and this frequency is nearly to it. And this is the S11. It improved so much, but in 900 megahertz it also larger than -10. So we make the proxy wider, and you can see that it's shifted to the right here. This is 900 megahertz and this is 850 megahertz. So we add the 3 fingers and 2 horns to make on this frequency lower than -10 decibel, and you can see that like -10 threshold. So the frequency is below this line. And this is the result. We use the network analyzer to measure, and we use MATLAB to compare the two results. The blue curve is the simulated result, and the red, the dot red, is the measured result. So you can see that as here, and all of these points are lower than -10 threshold decibel, and this is the result. But at 1800 megahertz, this result is bigger than our simulated. And you see the radiation pattern we use SMS to simulate. And this is 850 megahertz, the maximum gain is -8 decibel, and at 900 megahertz, the maximum gain is -2.2 decibel. And at 1800 megahertz, the maximum gain is 4.5 decibel, and it works like an omnidirectional antenna. So this is the summary of the antenna. This is S11. This is the maximum gain and the size. The size now is 34.26 millimeters. So we sent the design to VN Robotics program to design a ZDN receiver. So you can see that this antenna is integrated onto the PCB board. And we put conclusion. So our antenna is very small and it's ready for manufacturing. And because it's integrated onto the board, so that we can lower the manufacturing cost. Thank you for your attention.
Okay. We have the time for questions and comments, please.
That the second design is for matching 50 ohm and you increase the length.
Yes.
But in my opinion, I think if you want to change to match 50 ohm, you have to change the width instead of the length. Because I think the length impact on the face.
We try our mirror and we find that this side is physical.
Yeah, but it's not like if you want to design the transmission line for TPO, you have to calculate it. And the width is the important parameter, not the length. The length changes only the face. So yeah, maybe the width is good for your design, but the reason is not for change the TPO.
So maybe so when you extend the length, so it's rotate the point in the Smith chart. Because so at the first design, so the point at the output is not 50 ohm. I mean, so the transmission line will convert the impedance from this point to the other point. So when you extend the length, right? So it will transfer the impedance to from this one to the other impedance. It's the base point is richer. So therefore, to make the matching better, instead of the change width. So just happy to answer the question.
Yeah. But so that's transmission line, right?
Yeah, that's true.
You mean
But I think transmission line, the width is important.
Yeah, the width is
And
important.
the last year is only the place. How can you change to shift the switcher?
So, for example, you have the number 4, the quarter wave transmission line. You will transfer the open to the short, for example.
Yeah, but it's not a transmission line.
That is the transmission line.
No, I mean your opinion.
No, I mean 50 ohm transmission line starts from here, and this is not 50 ohm.
Yep.
That's why it's something like, transformer. Yeah, you have another 50 ohm. And you have some currents. If you already equip this antenna of the commercial GPS by the company, is it working?
Yes, it works.
Okay.
So well.
How is it is circular polarization, GPS. How is the polarization of the antenna?
I don't know the
Yeah, this is the linear form pattern. Are you measuring the circular polarization? This is linear polarization. GPS is using the circular polarization.
I do exactly, and my price is exactly. Yeah.
Okay.
I'm a senior student, so I take more or less about this, and I just learn how to design shape and one how to
This one is the main design. Okay.
decide to
Do you have some more comments?
Yeah, I have comments, not question. So the game you should use DPI, DP, or DPI, I think.
Maybe this might be the
Just comment.
DBI is circular polarization. You have some more? It's okay?
So
Okay.
do you have the graph there beneath the antenna?
no, I don't have the problem because I use the graph of the measurement connector.
And so the width of the input line is how much? You said you use FR4 1.6 millimeter, right? 1 millimeter.
Do you have any idea why the measurement result for the higher resonance point? It's not really so. I think it's shift into higher frequency. The measurement result. Do you have any idea why it shift to the higher frequency?
Because when design this antenna, I use I do it by hand, not use a machine, so the size is not good. It's not accurate.
Which part of the antenna affects the resonant results of this point? I mean, in the lower resonant points, they have not that much change, but in the
evaluation for this matching, which one? Yeah, you know, another slide.
I don't know how to lower it in the real antenna.
We go to the slide for the matching design for the higher frequency. Yeah. This one?
We control this to shift the frequency at 800 and 900 megahertz. To lower, we add to 3 fingers, 2 horns.
This is important for the design of this resonance. Okay.
Lower.
Yeah. In the simulation it works, but there might be some of the fabrication error or something. It is not so low. Okay. So do you have some more comments, questions? If not, I will close this session and we will restart the session from 10:45. So please take a coffee break. Starting. Okay. Thank you very much.